Yeah. Yes. Okay, right. What we're going to do today, I will recap a little bit of the things we went through yesterday. I pick out the more important parts, and then we're going to move on from page 23 onwards today. Okay, so we can use page 23 to recap whatever we did yesterday, at least the more important parts. Okay, just to mention a few things. Last lesson yesterday, we went through the mechanism. Okay, some of you guys may not be very familiar with the mechanism yet. No worries, we'll be doing more of it today. So you can see. Okay, the first time you'll see anything is always hard, but the second time onwards, usually it's a bit better. Okay, so quick recap. Yesterday's mechanism is called electrophilic addition. Okay, you are adding things onto the LP. Okay, so very fast few examples. The first one was with HX. Okay, you can just write this down and somewhere, maybe on page 19 or something like that. Okay, sorry, not 19, 23. We stopped off at page 23. Okay, so first one was with HX. So we went through the whole procedure, right? We have, let's say, an alkene, and this alkene, once you react with HX, you are literally just adding the H and the X onto the double bond. But can you see the double bond needs to break? Okay, because when you're adding new atoms, right, you need to break the bond stuff, of course. Okay, so that's what we did yesterday. This is the overall equation. Okay, then there's the mechanism and whatnot. The second one that we went through, right, is X2 in the elemental state. So it will be X2 in the liquid state or X2 in the initial state. Right? Okay, so same thing like what we did yesterday. You are just literally adding the halogens onto the double bond. So you see the double bond here. I'm going to break the double bond, and in response, I'm going to add 2 halogens onto that alkene. That's all I'm doing, and that's all we did for yesterday's lesson. Okay, but there's also a very crucial idea, and the crucial idea is here. If you all realize something, I drew this particular structure. Okay, but can this structure form as well? Simple question. Is this a possible structure that will come out from this reaction? Can also, right? Because all I said earlier is this. You are just taking the H and the X and just attaching it onto the double bond. Okay, just look at it closely. The double bond has a carbon A and carbon B. Let's just label these two. Okay, this structure that I highlighted in here is a structure that will form, also known as the major product. The one over here is known as the minor product, means it's the one that doesn't form as lightly. Can you remember the rule? What's the rule called? To determine who's the major and the minor product. If you don't know the guy's name, I say it's totally fine, right? Okay, it's called Markovnikov's rule. Let's just very briefly run through the explanation one more time, right? Before I can move on to our third reaction today, which is on X2 in the aqueous state. Okay, that's what we're going to be focusing on today. But before we get to this, let's recap your Markovnikov's rule and the explanation. Okay, then we can understand this a bit better. Okay, so I'm going to draw the mechanism, right, for this first reaction. Okay, recap the mechanism. In the first step, I'm going to take out the alkene, and I'm going to take out my H and let's say Now guys, remember, what's the rule for electron flow? Electrons must flow from where to where? Rich to poor, always. Okay, so who is rich? Alkene or the HBr? Okay, the alkene has a double bond is full of electrons, right? It's rich. And who does it attack? Who's poor? Okay, hydrogen. How do you know hydrogen is poor? What must you tell the examiner to show that it's poor? It has the partial positive charge because of electronegativity difference. Take the rich, so point from the alkene to the H, okay, because the electrons in the double bond must break, right? So it goes to H, this bond breaks and go towards R. Can you see that? Okay, so remember, guys, I'm going to label this as carbon A and B again, because I feel that yesterday maybe a bit shaky. I don't really understand Markovnikov's rule that well. So I'm going to spend a bit of time going through this again. Okay, can you remember, okay, this carbon here, these two carbons attack H, right? Now, which one does it attack? Okay, which carbon will bond towards the H, A or B? Okay, not sure. Let's draw again. Okay, let's just say carbon A is attached to the H. That means what must carbon B now have? A plus charge. Okay, good. How do we know that? Remember, when a double bond is broken, both carbons have one less bond, correct? And that's bad. Carbon must have 4 bonds. So carbon A, okay, look at carbon A first. Carbon A broke a bond, but it instantly got together with H. So did he lose any bonds? No, right? It got replenished instantly. But you see, carbon B is like, hey, bro, not fair. I broke a bond, but I got nothing in return. So he lost something, right? Losing something, you must gain a what charge? If you lose electrons, you have a positive charge. But on the other hand, when you gain electrons, you gain a negative charge instead. So you see carbon B, he's like, bro, it's not fair. I broke a bond for nothing. So now he has the plus charge. This is your carbocation. But another scenario could pan out as well, right? Carbon B now attaches to H. Okay, so this is the other structure. If carbon B broke the bond and got together with H, then carbon A must have the one. Carbon A now is the plus charge. Now it is A who says, bro, it's not fair. Why did I break a bond and not receive anything in return? Okay, so now I have two possibilities, but only one of them is more likely. So guys, how do we explain this phenomenon again? Which one is more likely to occur? Look at the major product. So from that major product, who is the one that's more likely to form? The left or the right? Okay, the right. Okay, as you can see here, the Br minus is eventually formed, and that will attack the carbon A to form the major product, as you can see on the board. You can see that? Okay, but how do we explain this? Okay, let's write down the explanation one more time. I know we wrote it down yesterday, but let's do it one more time. Okay, so now, what's the difference between two carbocations? We have to identify something first. This is a primary carbocation, right? Only have one other alkyl group bonded to it. How about the guy on the right side? Okay, secondary. Good. Okay, so we found that out. Hey guys, what is the special effect of an alkyl group? Remember? Good. Okay, alkyl groups, the only group that we have done so far are electron donating. So you all think about it as this way, okay? I need you all to pretend that the carbon with the plus charge is you. Okay, pretend that you are the carbon with the plus charge. Plus charge means you are rich or poor. Okay, very poor, right? Okay, so imagine this, okay, you feel very poor, you feel very desperate, very tired. Okay, but then on the other hand, guys, okay, you see this, given that alkyl groups are electron donating, is it better, right, if one guy gives you attention or two guys try to give you attention? Which one is better? Do you prefer one guy giving you attention or more guys giving you attention? Of course, more, right? The more the better, right? You want more guys to chase you, it feels better, right? So that's the idea here. You feel more satisfied, right? If more guys start to give you attention, which is your secondary carbocation. And because of that, what will happen to the plus charge? Given that you are more satisfied in this scenario, the plus charge becomes bigger or smaller? Smaller. You are now not as poor as this guy over here, right? I mean, fundamentally, both of them are getting attention from guys, but this girl is getting more. So in other words, this is the explanation here again, guys. Remember, you must first tell me that the secondary carbocation has more electron donating alkyl groups than the primary carbocation. So your very first point is to just tell me the difference between both carbocations. Okay, the more we write this explanation, the more we will understand this, right? Okay, so let's highlight the keywords more electron donating alkyl groups. Having more guys giving you attention means you don't feel as poor, as deprived as before. Okay, so take a look. What's the next thing you must say? What's the word for making a charge smaller? Starts with E. Disperse. Good. Okay, you want to disperse charges. You have to make the charge as small as possible. So guys, look at your diagram here. Okay, comparatively speaking, this guy's plus charge not very big, okay, very, very small, but this one comparatively is much larger. Because this one only have one guy giving attention. So it's quite not enough. One guy giving attention really not enough, not as satisfied. Okay, so that's the idea. You tell me that the positive charge on the secondary carbocation is dispersed to a larger extent. So refresher, very important refresher. Okay guys, why I say larger extent? Because both cases, right, okay, there are electron donating groups, just that this one has more, so it disperses more. Okay. So that what does this make the structure? Secondary carbocation is more what? Okay, you're more satisfied, right? So what does that mean? If the charge is dispersed to a greater extent, the compound is more what? More stable, exactly. Okay, you won't be as desperate as before. You feel more emotionally stable. Same idea over here. Secondary carbocation, right, is more stable and thus more likely to form. Remember the fundamentals of chemistry. Something that is more stable will be more likely to form. That's just a fact. Right? Okay, so that's what we are seeking to explain here. And that's why this guy here is the major product. The secondary carbocation is what I am interested in. Okay, so that's Markovnikov's rule in general. Markovnikov's rule looks at the most stable carbocation. Finish. Any questions? Okay. Okay, so with that said, okay, we look at page 23 now and 24. Let's draw a mechanism for x2 equals. Now that we've gone through the arrow movements one time, and now that we have gone through the Markovnikov's rule, I want you all to take a look at this rule. Yeah, you read this? Okay. Come. X2 equals, let's write a balance equation first. Okay, you all can write this in your next page, page 24. Okay. First of all, I'm going to use a bromine molecule, same as just now. I'm going to add bromine now. Okay, let's just use bromine in the aqueous state. Now, what's going to happen here? I want you to observe the final product. My final product looks like this. I give you all the final product first, so that later on, we shall see how the mechanism goes. Okay, this mechanism will be the most young. Okay, but the fundamentals are the same as before. Okay. Okay, again, what's the first thing you need to write down for your mechanism? Title. Okay, good. Then write down your title first. Yeah, I mean, you guys can spell the whole thing. Electrophilic addition. Okay, I'm just writing short form. Okay, once done, okay, you can write down your first step. Okay, just use put your reactants there. Okay, let me put one protein there first. Yeah, we are gonna keep looking at the final product in this equation. Now, remember, every time the product is here, right? Is it the major or the minor product? It's always the major product. So this is the most likely to form, and we are trying to form that only. Okay, come, mechanism-wise, what do you think I need to react with? Okay, alkene is electron rich or poor? Alkenes are electron rich, so you need to attack something poor. Now, you see, with aqueous, bromine aqueous, that means there's just one. Aqueous implies water, right? So now my solution contains Br2 and water. Now, since we have multiple species, I want you guys to tell me what are some possible places, right, where you have a poor region. Like as I said just now, HX, H is partial positive, X is partial negative, right? Any partial positive here, let's just identify in Google. Br, is there any partial positive? Okay, let's just put a Br here side by side. Br, and I draw water also. Here will be water. Okay, remember when you put Br like this, stand alone, it is non-polar, right? So it won't have partial charges. But if you put it close enough to a rich region, what will happen? The electron cloud will be polarized, and it will be repelled away, right? The electrons. So that means you will create a dipole on the spot as well. That's what we went through yesterday. A halogen that is non-polar, you place it close to the electron-rich double bond, electron cloud will be polarized. Okay, that's what we need here. Okay? Okay, so any other partial positive charges that you can see in these two elements? Any other partial positive charges? Anywhere? Okay, O is what partial? Negative. O more electronegative than H, right? So H is partial positive. Now guys, if you notice, there are two possible places in order for you to attack, right? But guys, can you look at the final product here? Okay, later if you have time to copy, okay, we take a look at this first. What do you think it attacked? Okay, it has to attack the partial positive charges, right? So did it attack Br or did it attack H? Okay, look at the final product here. Did the carbons on the propene attack the H? Okay, no, I actually don't have. You see what did the carbon attack? It attacked oxygen instead. You can see that. Okay, it didn't attack H. And you cannot attack oxygen because oxygen is considered rich as well. Rich cannot attack the rich, it's impossible, they'll repel one. Okay, but there's no way that this can attack H because it just doesn't show in the product. Does that make sense? Okay, so we don't see that. That means that it's not possible for you to attack water in this step. Meaning to say there's only one electrophile, which is your BR. Okay, so just attack the same as normal. Okay, I'm going to take the rich double bond, attack BR, and then what must happen? Okay, the electron here, the bond must break, right? And then the electrons go towards BR. Okay, so that's the first step. Okay, we explained why it couldn't have with water, because there's no such product. Okay, always stare at this final product. Okay, just don't have means don't have law. Okay, so this is our what step? Slow step, yes. Okay, there's a lot of breaking, bond breaking. Breaking up is very painful, very slow. Okay, slow step, right? Okay, now next, I want you all to tell me what's the carbocation ion that I'm going to form. Okay, same thing. I'm going to look at my carbons A and B. Where should the positive charge be? On carbon A or carbon B? Okay, good. I already told you guys you must look at your carbocation ion, your plus charge. It must be on A. Anyone disagree? Yeah. So positive charge on carbon A, that means carbon B must have what? The BR that you initially attacked. Don't forget that. Can see? Yeah. Carbon B got back his fourth bond. Carbon A broke his bond for no reason, so he lost something. Okay, what else is also formed? BR minus. Okay, he gained electrons. Gaining electrons is an example of getting a negative charge. So it all ties in so far. Again, I'm only interested in a major carbocation ion. Now let's look at the second step. Okay, draw your carbocation ion again. And guys, what do you think will attack this positive charge carbon? Something that must be rich, right? Okay, anything rich can attack this carbon with a plus charge. Agree? Okay, so any examples of rich things here? Okay, there's a Br minus that you produce. Okay, let's write that down first. Okay, so that's one possible answer. But guys, at the end of step 2, what am I supposed to get? I must get the final product here. But can you all see the Br, yes, I got that. Then what do you think must attack this carbon, right, in order to get that final? What else was also here in this reaction? Water. Okay, so why water? Okay, why can water attack this? If water can attack this carbon, it means water is an electron. What species? Electron-rich species, right? So Br is rich because it has a negative charge, it has lone pair. Oxygen on water also has lone pair, it's also rich. But end up we know there's this, right? Because that's the major product. But can I ask you guys why first? Okay, before we move on, why does water attack the carbon more likely than the bromine attacking the carbon? Any idea? Okay, so let's write this down somewhere else. Okay, why is it that water has a higher chance of attacking than Br minus, even though they are both equally rich? Okay, the keyword is that this is aqueous bromine. If water is the aqueous part of aqueous bromine, what's water acting as? Water is a what? Bromine aqueous. That means you take bromine and then you add water. So water is acting as a what? Good. Okay, water is acting as a solvent. So go and write this down. If water is a solvent, that means, guys, is bromine in greater excess or water in greater excess? Water, right? Guys, solvent must be in large excess. What? Imagine you try to make Milo, then you never put enough water. Then what the hell are you drinking, right? Okay, so water is a solvent, so water is in large excess. There's a much higher chance for water to be attacking than Br minus instead. But guys, is it possible for Br minus to attack? Is it possible? Entirely possible, right? Minus plus can attack one. It's just that it's not the most likely to form. I'm only interested in major product. Okay, so again, I don't need to draw the Br minus here to get erase this. Okay, I need you guys to draw the electron flow. Okay, so it's from where to where? Arrows must point from where to where here. Okay, so it's reached to pearl, right? Okay, so it's from where to where? Okay, the lone pair to the carbon with the plus charge. Again, guys, make sure you do not attack the positive charge. I need to see the lone pair, and I need to see you attacking the carbon, not the plus charge. Okay, you want to form bonds with the carbon. You don't form bonds with plus charges, no such thing. Okay, so just follow me through this. Okay, what's going to happen here? Carbon is going to be bonded to O, right? You can see that. So if carbon is bonded to O, Now, you see the O also has two more H's here, right? I'm just going to follow exactly what I did. Only one arrow, one action. Can see that? O bond to C, so it's O bond to C. That's it. I'm not going to do anything else. I know the final product doesn't look like this yet. But wait, one arrow, one action. Okay, now guys, take a look. The carbon here is poor. He only has the 3 bonds, right? Because he broke one for no reason. Now he got back his 4th bond. So does he still have the positive charge? No, no more. He got back his 4th bond. He's happy. Oh, okay, so far. Now next, oxygen. Does this look weird to you guys? Oxygen usually has how many bonds? 2 bonds, but now this dude has 3 bonds, right? Okay, so that means it's probably going to have some sort of charge. Plus charge or minus charge. Look at this idea here. Lose electrons is positive, gain electrons is negative. What is he doing over here? He is losing electrons to carbon, right? So that means oxygen now has a what charge? Plus charge. So clearly this isn't the end of the reaction yet. Okay? So this must be shown up. Okay, I explain again. Carbon no longer has the plus charge because he got back electrons. He's now not poor anymore. But then oxygen has just given something away. He's poor. He has plus charge. Okay, but eventually, guys, okay, let's draw out the final product. I just want this. I just want one O and one H. Okay, so what do you think must happen in between this process? What do you not want over here? You want to get rid of one H, right? Okay, so that means one of these bonds have to break. Okay, good. So we have that in mind now. Okay, one of these H's must go. Someone must come and take him away, right? Okay, he cannot be clinging onto oxygen for dear life. Who else do you think can attack this H to take it away? Exactly, good. Okay, I had Br minus in the background, right? So I want you to take your Br minus that you formed just now. This guy is going to come to the rescue. The rich Br minus, draw the lone pair, must attack the H so that they form what? What's the final product? H and Br forms HBr, agree? But then now that H is stolen away, what happens to these electrons? Cannot just be flying them. What must happen to it? Any idea? Okay, you'll see this slowly. Br comes to take away H. Okay, that's good. But the electrons here must go somewhere. Who needs the electrons? Anyone screaming for electrons because it's poor? Oh, he's right there asking you guys, hey, I'm poor, can you please give me the electrons? So, might as well just give him the electrons. Okay, so the electrons, because it's broken already, right? Give it to oxygen. He needs it. That's how he's no longer poor. He's now normal. He's now a neutral molecule. That's the full mechanism of this question. Again, I know it seems a bit overwhelming. No worries, we'll practice until it becomes okay. Okay, but you see the rationale behind all this, okay, it's all about electron movements. Any questions so far? Okay, those on Zoom, if you have any questions, just unmute and just ask. Okay. Yeah. Yes, okay. You're forming a bond. We'll talk about this. Okay, see H don't have electrons, right? The electrons is already in the bond. So it must go from the bond into oxygen. You have to realize bonds are made out of electrons. And arrows represent the movement of electrons. So you cannot point from H, because H don't have electrons. H only have one, and the one electron is already here inside. So it must go from electrons to O. You see that? Yeah. Okay. This one affects H because you want to form a bond with H to form HBr. But once H is gone, you cannot attack from H1. It must be from the bond. Bonds are made out of electrons. Give these electrons to O. Okay, all good? Okay, so that's the mechanism for this. Okay, the next page, 25, also pretty much talks about whatever I just discussed. Okay, so to summarize again, this thing here is called a bromohydrin. You don't really need to know the name. I mean, it's good to know also, but not very important. Okay, you add a PR and then you add the OH. You can see that. Okay, look at the overall product. The OH is added to a more stable carbocation. Okay, the first step is the same, only the second step is a bit different. Okay, and with that said, there's a question that we need to discuss. Can you look at page 26, the first question on top? Okay, this one quite important. Okay, guys. Alkenes are more reactive towards Br2 aqueous than Br2 liquid. Okay, I'm going to rephrase the question a bit, so you'll just look at the board here. Okay, Br2 aqueous is faster than your normal Br2. So your Br2 is CCl4. Okay, this is the question we're going to discuss. Okay, Br2 is CCl4 and Br2 liquid is the same thing. Okay, so let me just add on to this. Sometimes you can see X2 is CCl4. Okay, CCl4 is just another type of solvent. Okay, but it's the same as your second one. Hope with that. Okay, so this is what they're trying to ask us to explain. Somehow, if you use aqueous bromine, the whole electrophilic addition is faster. Now, guys, when you see the word faster, you think of what concept? You think of the rate of the reaction, right? Guys, how do you affect the rate of a reaction? Okay, the rate of a reaction, okay, to be more specific here, can you look at this mechanism that we drew just now? The slow step or the fast step will affect the rate. Slow step, good. Okay, the slow step is known as the rate determining step. So I want you guys to just look at this. We have to only be focusing on the slow step because that's the only thing that's affecting the rate of the reaction. And guys, what's the difference between Br2 aqueous and Br2 is CCl4? Aqueous means what again? In water. CCl4 is just another solvent, right, guys? What's the difference between these two solvents? Water and CCl4. What kind of solvents are they? Water is a what kind of solvent? It's a polar solvent, right? Whereas CCl4 is a non-polar solvent. Okay, so guys, somehow this polarity of the solvent will affect the rate. You can see this so far. I placed out the difference. Polar solvent, non-polar solvent. Somehow polar solvent is faster for some reason. Okay, but look at this, guys. Can I say that, oh, water is polar, so it's faster. CCl4 is non-polar, so it's slower. You take a look at this. Rate must be looking at the slow step. Does water or CCl4 ever appear in the slow step? No. What appears in the slow step instead? Your Br2, right? So guys, you cannot talk about H2O and Cl4 directly. Go write that down. Okay? Cannot talk about, it is not the answer, but just note, cannot talk about CCl4 or water directly. Why is that so again? As they are not in the what? Yes. They are not in the slow step. So how on earth are you going to affect the rate? As you can see here, water appears in the mechanism, yes, but water appears in a fast step. Again, fast step don't affect rate. So that's what we're trying to understand here. Somehow, if we can't talk about them directly, somehow the CCl4 and water will somehow affect the Br2. Because remember, Br2 is in the slow step. So it's about the solvent affecting the Br2 instead, not about just the solvent. Can see what I'm trying to get at? Okay, it's not the solvent that makes it fast or slow. It is the solvent affecting Br2 that makes it fast or slow. Okay, so let me just erase a bit here. Okay, then at the bottom, let's just draw in a small little diagram here. I can have Br2 getting affected by CCl4. I can also have Br2 getting affected by water. Okay, just now we mentioned CCl4 is not polar, H2O is polar. Okay, H2O is polar because clearly there's this, right? Okay, there are partial charges. Now guys, if you all notice something, okay, partial charges are there on CCl4. There are no partial charges here, right? Because it's not polar. Okay, take a look at this. H is partial positive. If you put this close enough to Br, what will happen? Okay, it will also, okay, Br by itself is already polarized, right? When you put it near an alkene, it will polarize the electron cloud of bromine. That's what we discussed earlier just now, right? But in addition to that, can you see what will happen? If you put a polar solvent, what will happen? Can you see that the electron cloud of bromine is also further polarized by water? I say again, come. Okay, alkenes can polarize the electron cloud of bromine. Same. But now there's also water that will help to polarize this to an even larger extent. So in other words, I want you to do this. The Br now has an even greater difference, right, in electronegativity. It is more polarized than just with CCl4. Can see that? So to summarize everything, this is the answer to this question. Water is a polar solvent. You just specify first. Okay, while CCl4 is a non-polar solvent. Having an additional polar molecule, right, will actually polarize Br even more. Okay, again, I'm talking about Br because Br is the one that's in the slow step that will affect the rate. Okay, so H2O will polarize the electron cloud of bromine to an even larger extent. Okay, so it pulls the electrons even more towards the right hand side. Okay, so can you tell me which bromine is poorer? They are both poor, but which one is poorer? Top or bottom? Sorry? It should be the bottom, actually. Can you see? This one will polarize electrons to the right, right? This one also polarized to the right, but you'll go right even more because of a polar molecule. See, this partial positive is trying to attract electrons to the right hand side as well. So that makes the bromine on the left even poorer than before. That's why I put 2 positive and 2 negative charges here, just as a visual representation. There's a greater polarization in this case to the right hand side. So that means this bromine is actually more poor. You can see that? If you're more poor, are you going to get attacked faster or slower? Okay, the more poor you are, the more desperate you are, right? Let's just say some deprived of attention. You need that attention, you're craving that attention. That's why you're very, very desperate, very reactive. So that's the idea here. If the electron cloud of bromine is polarized to a larger extent, okay, bromine will become more electron deficient. And as a result, more reactive. So that's why if you use water, right, it's actually faster. Okay, anyone still not very sure if this need to explain again? Any part they need to explain, right?
Wait, Kai-sheng, how come the CCl4 can polarize?
CCl4 is non-polar, so the effect isn't very strong.
Oh, I thought only polar molecules can.
Yeah, polar molecules can. That's why over here, okay, H2O will be polarizing the electron cloud of bromine to an even greater extent. Why I say to a greater extent is because it's already polarized by alkenes. But if you put another polar molecule beside it, it's just going to polarize it even further. You can see that?
Oh.
Okay. CCl4 doesn't exhibit a very great effect. So the polarization here is only from the alkene. The CCl4 doesn't add on to it. But water adds on to it. That's why bromine becomes poorer than before.
Okay.
Right? Yeah.
Right.
Okay, all okay this? Can? Okay. Right. We're going to discuss another scenario. Okay. And this scenario, okay, don't really look at the notes one. Okay, I want you to look at the one on the board. Right? So I'm going to write down the question. Okay, so let's just say I have propene, and now I'm reacting this with bromine aqueous with NaCl. Okay, guys. I want you guys to show all the possible products that will come out from this reactor. Okay, we don't look at the question and the notes. Okay, we just look at this. Okay, can we identify first? We have bromine aqueous and NaCl. Can we just identify everything? What are the things inside this reaction? Okay, we have bromine, right? Anything else? Okay, we have water. Anything else? Okay, this one can we split? Okay, we got Na plus and Cr minus. Okay, so let's just see. So many reacting species, right? Okay, there's just one of them that we should cancel out right now. Okay, and the guy that should cancel out right now is Na plus. Any idea why? Okay, again, you see, you're forming bonds, right? Have you ever formed a covalent bond with a metal? Okay, no. Okay, so we get rid of Na plus first, that's not significant. So we are just focused on Br2, water, and Cr minus. Now come, let's look at the first step of the mechanism. This is electron rich. You must attack something that's electron poor. Okay, look at all the things here. What are some poor species? Does Br have a poor region? Have, okay, like what we said, you put Br close enough, you will have partial charges. Any other poor stuff here? Okay, Cl minus poor. Okay, Cl minus means rich, right? Okay, so cannot be. It cannot be Cl. Okay, so you have Br. How about water? Anything about water? Okay, H is poor, but does it affect H from what we went through just now? No, so there's no water here, it's just bromine, correct? Bromine was the only poor species that we went through just now. So the first step is just going to be this one. Okay, whatever we did just now, correct? Okay, can someone tell me where is the carbon going to be at? Sorry, where's the positive charge going to be at? A. Okay, is he getting used to this? Okay, good. So if the positive charge is on A, that means carbon B must have the Br. Okay, carbon B got the Br, carbon A broke the bond for no reason. Okay, then I also form Br minus. Agree? Okay, come, let's look at the second step. I'm going to take out my carbocation. And let's just see, now that this guy is poor, we need something that's what? Rich. Okay, let's find all the nucleophiles. What are some rich stuff? Can we list down everything that's rich here? Okay, there's Cl minus. What else? Okay, there's Br minus. Okay, good. Anything else? Okay, water as well. Okay, we mentioned just now that water has a rich portion on oxygen, right? Okay, wow, so many nucleophiles. Okay, they are all possible, correct? Because as long as you have a rich and poor, you can attack. Agree? So let's draw all the possible species here. Okay, we can have Br with Cl, Br with Br, and then Br with OH. Okay, let's just skip all the arrow drawings and all that. And see that, okay, so these are some possible structures. Okay, now I'm going to give you guys 4 options, and I want you to tell me which one is the odd one out. Okay, so take a look. 4 options. Just tell me which one just doesn't form. Okay, take a look at these 4 options. Can you tell me which one cannot form? Okay, can the first product form? Oh, it's part of it, right? Okay, so this first one can definitely form. Okay, the second one down here cannot. Okay, so is it the same as this one? Are they same products? No, okay, the position has swapped, but is it still a possible product? Okay, remember the products that we drew over here, right? These are the major products, right? Because this carbocation is the most stable carbocation that you can form. Okay, so if let's say you don't form the most stable carbocation, right? You can still form this product here, if you realize. Okay, they just swap the positions, but it's not as stable as this one, right? Okay, the ones that we drew here are the most stable ones. Okay, can this product form? Why cannot? You realize there's a pattern, right? There's something in common, right? Out of all the products that we've drawn. Yes, guys, why is Br a common thing in all our products? Because look at the mechanism. What happened in the first step? Yes, no matter what kind of nucleophile attacks in the second step, in the first step, you're always attacking only one electrophile. This is the only electrophile that you need to attack in the first step, right? So that means your product must have a Br minimally. Can you see that? Okay, so we're writing this down. Okay, you must have a Br electrophile. If there's only a one electrophile, that means your products must have Br, right? Okay, so we'll write this note. Actually, this question over here is very simple because you just need to spot this pattern here. Identify the electrophile first. It's bromine. That means your product must have bromine, minimum 1. So just based on this information alone, which one is not possible? This guy, not possible. So the answer to this question is C. I know it's printed in the notes for some weird reason. Okay, but I think you all understand this. Okay, so I'm going to draw all the 4 products also, because that one is not spherical. Okay, so I say again, no matter what kind of nucleophiles they can add Cr minus, they can add water, everything. Everything is possible. The only thing not possible is if you don't have the electrophile inside. All good? Okay, take some time to copy. Right, any questions so far? No? Okay, once we're done with this, we're going to move on to the next page. Okay, my goal is to finish all of this by today, so you'll see the page, then you're like, shit, so many. Cannot. Okay, we'll do this together. Right, okay, page 27 is actually, I can go through this within like 1 minute. Okay, on page 27, I just need all the take note. Okay. I mentioned that electrophilic addition, right, got 3 types. We have gone through all 3 types. These 3 guys need mechanism, so you need to know how to draw the mechanism and all that, arrow movements. Okay, but for the next 2, they are kind of like, you don't need to draw the mechanism one. Just need to know how the reaction works. Okay, so I've divided this up. Electrophilic addition got another 2 more. One is with water. So what's going to happen here is this, just observe. If I take an alkene and I react it with water, I will get this thing called alcohol. Alcohol is OH. Okay, why? Because I add the H to one carbon and the OH into the other carbon. That's it. So that's what I form. Okay, all you need to highlight here are the reagents and conditions. Basically, the recipe for this to happen. Okay, there are actually 2 methods here. So you can choose either one. Doesn't matter. They will never ask you, oh, you must use this method. No. You just choose whichever one you want. I'll prefer the industrial method because it's only 1 step. Okay, the lab method, there's like 1 and 2, which I hate. So I just like steam H3PO4 catalyst, high temperature and pressure. You just need to write it in exam. Like for example, they give you this equation here, and they ask what's the reagents and conditions required for this to happen. Just copy that out. Okay, so as you can see, there's a lot. Then you need to slowly start to memorize. Okay, we'll have a plan for that. Okay, come just turn over to the next page. Okay, on the next page, this is with H2 gas. Now, if you add hydrogen to something, right, it's also known as reduction. So I want to take note. Okay, there are 2 reactions here, either addition or reduction. Both are acceptable. Okay, addition or reduction. Now let's see how this reaction goes. I take an alkene and I react it with H2 gas, and guess what's going to happen? What am I doing here? You see the pattern across all the addition reactions, right? So what do you think I'm doing here? H2 gas. Okay, just add 1 H2, each carbon, right? Okay, and at the same time, what must you do after you add? You add H here, then you must break the double bond. Yes, okay, so we're going to break the double bond. I'm not going to draw the H's because they are meant to be visible. Guys, what functional group is that? Alkane. So in other words, guys, you can actually reduce an alkene to an alkane. Now, more commonly, this is known as the reduction reaction. You can reduce alkenes back into alkenes. So we are linking stuff up together. Okay, again, reagents and conditions, just go and highlight that. That one must be written. You need H2 gas, but you need nickel catalyst, high temperature and pressure. Those are just what you need to copy and paste. Okay, so with that, that's all the reactions for electrophilic addition. Good. Now, on the next page, okay, turn over now to page 29. We have a very it is a slightly different reaction. Okay, it's called elimination. And guys, if you can remember, elimination and addition are actually just opposites. Yeah, okay. You add, then you can take away also, right? Add and subtract. It's the same idea here. Okay, so for elimination in particular, to just lay down a very important fact, you are getting rid of hx. Okay, write it down first. Very important. I know addition, we added many different things. But for elimination, we only know how to get rid of hx. So guys, take a look. I can't get rid of two halogens like this guy over here. We will never learn that in our syllabus. Elimination must be for hx. Okay, let's see how this works. Okay, I'm going to draw for once. I'm not going to draw the skeletal formula. I'm going to draw the one that you see here. Okay, so this right here is one of the products that you can see up here. Okay, X and H, then H and BR. Okay, elimination is the opposite. So what will I form? Opposite of this. So what will I form? Okay, I'm forming back the double bond and HX lah. That's it. Okay, and I just need you guys to highlight where the H and X come from. Okay, so you look at this. I'm removing a H and a halogen. So the halogen go and circle. Obviously, you need to remove a halogen, right? But guys, where do you remove the H from? There's so many H's. Just take any one. Can? Is there a certain rule over here? Can I remove this H? Okay, you look at this. If I remove this and I remove this, how many bonds does the carbon on the right now have? 2 bonds. By adding a double bond, does that help? If you add a double bond in the middle here, does it become back to 4 bonds? No, right? You only have 3 bonds. So you notice, look at the final product. There still must be 2 H's on the carbon on the right hand side. Correct? So where must the H be removed from? Yes, good. The H must be removed from a carbon that is adjacent. What does adjacent mean? Just means next to it. So do not remove hydrogen and bromine from the same carbon. Go write that note for yourself. Do not remove H and Br from the same carbon. Wrong. Do not work. Must be from the carbon beside. So look at the carbon beside. It can be any one of these 3 hydrogens. It doesn't matter. Let me just choose the one at the bottom. Okay. Because guys, if you notice this, you remove 1 atom each, they can replenish that missing bond with 1 double bond, right? At the end of the day, all carbons must have 4 bonds. So you must remove 1 from each, then 1 double bond can help to replenish it. Okay? So you look at some practices. Okay, here very easy because I drew out the displayed formula. I'm going to draw skeletal and then you guys will slowly need to see how this works out. Okay. Okay, so let's look at another example. Find space to draw all the examples up. Okay, guys, can you just tell me how do you draw this product? Okay, when this guy undergoes elimination, you must remove a H and an X, right? Yeah, I remove the bromine, but where must the H be removed from? Is it from this carbon? Must be from the left. Okay, let's try the left. The left has carbon. Is there a hydrogen on the left? Have. So I'm just going to draw a 1. Okay, so let's just remove the H and the Br. So where's the double bond now? Okay, on the left hand side here. Right? Okay, guys, can I remove from the right hand side also? Because it's beside. Okay, if I remove from the right hand side, what's the structure I'm going to get? Like that, right? Is this another structure, another new structure? No, this is the same as before. So guys, just going to remove from one side, can really. Okay, then this is your P. Yeah, simple as that. Okay. Now, before I look at more examples, I need you all to highlight the reagents and conditions again. As you can see, different reactions for different stuff. Okay, here this is quite important. Elimination, you need to use this thing called ethanolic, NaOH, and heat. That's the condition. Guys, what's ethanolic? Okay, go and take note. If you're not sure. Ethanolic means it's a solvent. The solvent is alcohol or ethanol. Ethanol and alcohol, same thing. So I dissolve NaOH in not water, but alcohol. And that will cause the, okay, if you put aqueous, if you dissolve this in just water, another reaction will happen, which we will learn in a few topics time. So if you want to force elimination to happen, right, you must use ethanolic NaOH. Dissolve NaOH in ethanol. Okay, with that? Okay, so that one next time we'll look at the difference. Okay, let's look at more examples. Okay, how about this one over here? Okay, how do we eliminate this guy? Okay, find a H and a Br, right? Okay, circle out the Br and then. Okay, where's the H? Is it from this? Okay, no, not from the same carbon. Then must look at B side. B side only have one carbon here, right? Is there any hydrogen here? No. So there's no hydrogen on the carbon B side. So this cannot happen. So must look at it very closely. Okay, no elimination can happen because the adjacent carbon has no H. So that's the criteria for elimination. You must check that the carbon beside has a hydrogen. Okay, then. Okay, we'll look at more examples. Okay, not to worry about that. Okay, can you turn over to the next page? Okay, they say something about this rule called ZZ rule. Okay, it's not that important. Okay, you don't actually need to know that. Okay, you only need to know Markovnikov's rule. This guy says that. Okay, I'll just explain how it works. Okay, turn over to page 3030. They ask us to draw a diagram illustrating ZZ rule. Okay, no worries, there's no explanation here. This one just use eyes only. Okay, so let's see. I want you all to draw this structure. 2-bromobutane. Okay, and we are going to draw all the possible products of elimination. Okay, so I'm going to add my ethanolic NaOH and heat, and this will force you to remove your HX. So guys, give me one possible structure here. Okay, let's do our elimination. Br must go. What else? Hydrogen from where? Okay, let me just number 1, 2, 3, and 4. From which carbon? Hydrogen must come from. Is it carbon 2? No, not the same carbon, so where? Okay, carbon 1. Does carbon 1 have hydrogen? Have. Okay, so that's one possible structure. I remove from carbon 1, so where's my double bond now? In between 1 and 2, right? Okay, so there's one structure. Here. You get that? Is that the only structure though? Because why? I can remove from 1, which is this, or I can remove from 3. It's still beside 2, right? Does he have a hydrogen? Yes. So as long as you are inside something and that something has a hydrogen, you can undergo a elimination. So you get something like this. Double bond in between 2 and 3. Clear there, right? Okay, then what's next? Okay. Any other products? Okay, so okay, there's HBr, but I'm talking about the main product. Okay, you will get HBr. Yeah, I can remove from 1, I can remove from 3. Can I remove from 4? No, 4 is not beside 2. Okay, there's only 2 beside. There's only 1 left and 1 right. So you should only get 2 products, right? But take note, there's actually a third product here. And a clue is it's an isomer of one of these products. Any guesses? Is the cis isomer. Good. Which one can undergo cis trans isomerism? Okay, first one definitely not. Same hydrogens. But this one can definitely undergo cis trans. Here, this is the cis or trans currently. This is the trans isomer. So that's why there's actually a third product, the cis isomer. This is a very common question. They will tell you guys draw all 3 products. Then you'll be like, what the hell? Why is there 3? There's only 2, right? There's only 1 at the left or 1 on the right. Okay, but there's actually 3 because of the cis isomer. All good with this? Now, normally we'll stop here for the question, but we actually want to explain a little bit more. Okay, here we're trying to illustrate this thing called ZZ rule. Now, you don't need to know the definition of it. Okay, but let me just briefly write down. For ZZ rule, which I don't even know how to spell, this guy says the more alkyl groups, the better. More alkyl groups, more better. Okay, that's all you need to know for this. More alkyl groups on what? Okay, it's more alkyl groups on the double bond. So guys, let's count now how many alkyl groups are there on each of these structures. Okay, do this with me. On the left structure here, guys, how many alkyl groups are there on the double bond? So look at the double bond here. How many alkyl groups are there? Perhaps if I draw all the hydrogens out on the double bond, you all can see. How many? There are 4 groups, right? 1, 2, 3, 4, but how many are alkyl groups? Okay, it's just one alkyl group. Can see why? H, H, H. These are not alkyl groups, but this is a group of alkyls. Can see that? Okay, don't count them separately. We are looking at alkyl groups. Okay, so this is one group. Can see that? Okay, so in other words, when you erase this one only has one alkyl group. This one how many? Look at the double bond. How many alkyl groups attached to this? 1, 2. So 2 alkyls. Is that it? How many? 2. So in other words, guys, which one is the least likely to form? This is the minor product. Okay, that's what says rule says. Okay, but there is something even more interesting over here. Okay, so can you all see this? These 2 guys both have alkyl groups. So can we tell which one is more likely to form based on just this stupid rule here? Cannot, right? Okay, because they have 2 alkyl groups. But I can tell you guys one thing. I tell you the answer first, that the trans has a higher chance of forming than the cis. This is the most likely to form. This is the major product. Any idea why? Okay, this one probably don't know, but any smart guesses here? Can you look at the difference between a trans and a cis molecule? The trans is more likely to form than the cis. It's nothing to do with the alkyl groups, but it's more to do with its structure. Okay, something along those lines. Not really. Trans is opposite sides of the double bond, right? Cis is on the same sides. Guys, look at this. If the groups are opposite versus the groups on the same side, which one, right, is more spacious? Okay, opposite sides, right? Okay, so this cis over here, having 2 groups on the same side is not spacious at all. And that one will actually result in repulsions. So let's introduce a new term here. Okay, this one quite good to know also. Okay, they will test eventually. The cis is like that. The 2 alkyl groups are on the same sides of the double bond. And because they are on the same sides, as compared to opposite sides, it is more cramped, right? More crowded. What's the idea of crowded? Okay, take note of this word. The cis isomer faces more steric hindrance. I introduced this new term. You eventually need to use this. Okay, so let's explain. The meaning is just very cramped. Can see why this is more cramped than this. Okay, you stand opposite someone else, is definitely a lot more space. Okay, steric just means space. And you all know what hindrance means in English. You hinder something, you obstruct lah. So it's an obstruction of space. You have 2 people standing on the same side. Why are you doing that? So crowded. Okay, you are hindering the space. Okay, so more steric hindrance, guys, is this a good thing? Is this favorable? Having more crampedness? No, okay, it makes the compound actually less stable. Okay, so actually cis is less stable than trans. That's why trans is the most major product to form. So I give you guys a little bit of extra stuff here, but it's not really extra because eventually you need to learn this also. Okay, right? Okay, so eventually elimination, 3 products here. It's the opposite of addition. Or yeah, okay, go ahead. Okay, any questions so far? If you don't have, we're going to move on to the final portion of this chapter. Okay, this is on oxidation. Okay, can you look at page 31?
Wait, Kaisheng, so alkyl groups is the line?
Sorry, again?
What is alkyl groups? Is the line, is it?
Alkyl groups are just made up of, okay, take note. Alkyl groups are just made up of carbons and hydrogens. So this whole thing over here is an alkyl group because it's made up of 2 carbons.
Oh, okay.
These are also alkyl groups. It's just that these alkyl groups are only made up of 1 carbon. As long as you have carbon and hydrogen, you are considered an alkyl group. This one also have 2.
Got it.
Yeah, okay. Carbon hydrogens is called a group, alkyl group. Okay, any further questions? Right. Okay, so we're done with addition, we did elimination, finally oxidation. Now this one quite different from what we saw so far. Okay, so let's take a look. Okay. Okay, so what's mild-oxidation? Okay, first of all, oxidation got two types. There's mild and then there is spicy, right? Okay, they are not strong. Okay, there's mild and then strong. Okay, we'll look at strong later. Okay, look at mild first, mild, very simple. Okay, so I'm sure you can already imagine, right, the extent of these oxidations, the mild versus strong. Okay, let's lay down a few facts first. If I take an alkene and I undergo mild oxidation, okay, sometimes you all will see this symbol or O with a bracket that represents oxidation. What I'm going to do is I will actually take I'm going to break the down bond there and just add OHs to both carbons. That's all you're doing. No mechanism, none of that nonsense. That's all you're doing here. Just know the product. This is known as a diol. All means alcohol. Di because two lah. Okay? Yeah, that's all this does. Finish. Okay, oh, not finished. Okay, there are some other details we need to talk about. Okay. Now, the recipe for this, reagents and conditions, so things are very important. KMnO4, because guys, KMnO4 is a what? Oxidizing agent. Okay, now when you add KMnO4, you need to either have H2SO4 or NaOH. Yeah, just use H2SO4. I think the notes write NaOH is fine. I prefer H2SO4 because there are less observations. You will see why later. But most importantly, cold. Okay. Now, I want you guys to notice, can you all see why cold is mild oxidation? Okay, can you all see what's happening here? You're adding the OH onto both carbons, right? But at the same time, what else is happening? What bond is broken? Is it double bond meaning the whole thing? Right? But what exactly is the bond that's broken here? Is the whole bond broken? Is only the what bond that's broken? What's this bond called? A double bond is made out of one what and one what? Yes, good. Okay, it is the pi bond. Okay, one double bond is made out of one sigma and one pi, right? Which one is stronger? Sigma or pi? Okay, sigma is stronger. So guys, because this is mild oxidation, pi being a very weak bond, it will be broken. So guys, look at this. I must highlight a lot cold. Cold implies the conditions not very strong, right? So that's why you can only break the pi bond, which is considered rather weak. That's pretty much it for mild oxidation. Okay, you all can look at the observations as well. When there's oxidation, what will happen to KMnO4? It's not you should know also. Okay, the purple KMnO4 will turn colorless, decolorize. Yeah, that's the idea. No? Yeah, I'm not going to write that as in notes. Okay, that's mild oxidation in a nutshell. Any questions? Say again now. You're turning this into a diol. Break the pi bond, add OH onto both. That's all you're doing here. Okay? Okay, next up, let's look at page 22. Now that we're done with mild oxidation, I'm going to look at this thing called strong oxidation. A more common phrase that we're going to use here is called oxidative heaving. So this is a more legit term, okay, as weird as it sounds. Okay, so what's cleave? Okay, you know what cleave means in English? Cleave means to break something, to cut something. Okay, so I'm going to cut the compound. Okay, that's what we're going to do here. Okay, so take a look. If I bring out the same compound here, okay, this one is not a very good representation of the whole idea, but let's just see first. Okay, how many carbons do you all see here? Okay, 4, carbon 1, 2, 3, 4, right? Okay, what I'm going to do here is this. I will cut the entire bond because it's strong. Because strong means can break the whole thing. Okay, when I break the whole thing, I'll have how many products? Is it just one product? No, you break something, you cut something, must have multiple products, right? Okay, how big are each product? The product on the left has how many carbons? Okay, just 3, right? And then the product on the right has just 1 carbon. Okay, so 3 and 1 more, that's the idea. Okay, let me show you guys what these two turn into. The 3 carbons here will turn into this. Okay, I'll explain later. And then the final carbon will actually just become carbon dioxide. Okay, I'm trying to highlight one thing first. Okay, don't care about the products yet. I'll explain slowly later. As of right now, you just need to know that when you break alkene, you are cutting into multiple compounds. multiple smaller compounds. Cannot be bigger, right? Okay, because it's quite smaller, right? Okay, so a few things are reagents and conditions. You also need an oxidizing agent. You need an acid or base for it to work. And guess how, guys? What do you think is the condition here? You use coal. If you want to break the whole thing, you must heat. Yes, okay. You need heat here for it to be strong oxidation. And it makes sense, right? Because you are not just breaking the pi bond. What are you breaking? You are breaking the entire double bond, both sigma and pi. So you need something stronger for that to happen. Make sense? Okay, so most of the oxidation we're going to learn is oxidative cleavage. Okay, not really about our oxidation. The one not very simple. Okay, now finish it. Now, because we form multiple products, I need to teach you guys, right, how to determine what the products look like. Okay, there are some cheat codes, some rules over here. Okay, any questions so far? Now, if you don't have, okay, I will look at multiple examples. You all can see if you find any space, just write down all these examples. But first of all, go over to page 30. Okay, go over to page 33 first. This is the guideline, right, on how to determine what the products look like. I just need you guys to focus on acidic conditions. Don't look at alkaline conditions yet. Okay, that one you're not very sure, don't look at it yet. Okay, so under acidic conditions, this is what's going to happen. Let me just copy down whatever the post have written also. Okay, if you cut a double bond, and that carbon, right, okay, cutting is usually represented by the squiggly line. Okay, you cut already, right? And if the carbon has two H's, it will turn into carbon dioxide and water. That's what they mentioned. Later I'll show you guys how it works. Okay, you have another one. Instead of having two H's, now I have one alkyl group and one H. Okay, I know it's very difficult to see now. Okay, never mind. What's going to happen is this. Okay, actually just write all three up. Okay, you can also have the third scenario where you have two alkyl groups and zero H's. You will only see these three scenarios. Can see that? Now, I want you guys to write down the steps for this. 2 steps. Write it at the top. To determine how the product looks like, number 1, I need you guys. Okay, let me cut this. Okay, number 1, once you cut the double bond, you add oxygen to the double bond. It is after you cut it up. You must see the double bond always add an oxygen. And number 2, if there is hydrogen, you also add O to it to form what, guys? Hydrogen and O also becomes OH law. You see OH. That's it. That's all you're doing for. Nothing else. So come, let's look at the 3 things over here. Let's try to see how they derive all this. I don't want to look at the first one yet. I'll come back to this. Look at the second one first. You cut the double bond, then must do what to the double bond? Add an O. Clear? Is there H on this carbon? Okay, so what do you do to the H? Turn it into OH. How about R? Do you do anything to the R? Did I tell you guys anything about R? No, so don't do anything to it. That's the answer. And guys, this is known as you see this, I'll recognize this, start to recognize. C double bond O and OH is known as a carboxylic acid. Okay, there are only 3 products here. Let's figure out all these 3 products. Look at the last one. Okay, what do you do first? Double bond, cut already, add the O. Any H's? So what do? Do you do anything to these guys? Just copy them out. If you just see a double bond O only, this is known as a ketone. It's another functional group. Again, I don't expect you guys to know the names of all this. I just need you to know how to get these structures. Follow those 2 steps. Okay, finally, this one. What do I do again? Add an O then. Okay, the H have OH. Is that it? Another one. Okay, if you all realize what's the molecular formula of this compound? Okay, H2CO3. You all have seen this in acid base, right? This is carbonic acid, and this will turn into what? Exactly. That's how they get carbon dioxide and water. It still follows the rules. It's just that carbonic acid is kind of unstable. It will dissociate into carbon dioxide and water. So we have 3 products. You will form carbon dioxide, carboxylic acid, or ketone whenever you undergo oxidative rate. Again, this one not enough. We need to practice more of this. So I want you guys to find some space because I'm going to give you guys examples and I want you to draw out the products. Okay, let's start off with something easy. This one. 3 carbons only. Okay, instantly skeletal formula. What are the products here? Okay, draw this out first. I want you guys to first of all cut like that. If you notice something, I'm only concerned with the carbons on the double bond. So I'm going to number this carbon A and B. I don't care about the carbon on the left. It's not part of the double bond. Okay, guys, let's do carbon A first. What should you do to the double bond after you cut? Okay, look at A. Add an O, then anything else? Does it have a H? It has a H, right? So it becomes OH. This is a carboxylic acid. Okay? C double bond O, OH. C double bond O, OH. So that's carbon A. Okay, I want you to write A and B and all that out. Okay, because it helps you see what it becomes. So guys, how about carbon B? What does it turn into? Okay, it has how many H's? 2 H's, so it's which one? 2 H's, so it's carbon dioxide instantly. You don't need to draw anything in the middle here. You must draw the final structure. So it's just CO2 and H2O. So every time you see carbon with 2 H's, it's turned into carbon dioxide. Okay, so this is carbon B, this is what carbon B is turned into. Okay. I'll give another structure. Let's try this. Now we do this together. Later on, I'll let you try more structures. Okay, cut with your squiggly line. And then which carbons am I interested in? Am I interested in like this carbon here? No, I'm only interested in the carbons in the double bond. So same thing, go and label your A and B's. Okay, we do A first. What should we do to get A? Or perhaps another thing that can make things easier also. I'm going to do this. Okay, you all imagine. I'm going to imagine you take a piece of scissors, right? And just snap this into half. So I get 2 fragments, right? You see that? Can see that? These two? Okay, it's just a gap in between now. So I just snap it into 2 first. We do this first, sometimes it will help. Okay, next, what do we do to the double bond rule? Okay, add a O. You have another one, add a O also. Okay, you have any H? So it becomes. Here any H? No, okay, all these are alkyl groups. That's it already. So those are 2 structures. This is a ketone. 2 alkyl groups is ketone. 2 alkyl groups, the double bond O. Okay. So again, this is carbon A, it became a carboxylic acid. Carbon B became a ketone. Okay, find some space. I'll give you one more example, a bit longer, but try.
Wait, Kaishan, I don't understand how the B becomes CO2. Is there any to memorize?
B, this one is it?
Yeah.
Okay, because, oh yes, you don't understand this, is it?
Yeah.
Okay, because I follow the rules. Double bond, if you have 2 H's, double bond must add O first. Anytime there's a H, you become OH. H become OH. H become OH, correct?
Yeah.
This is actually H2CO3. This is a weak acid, and it will actually just dissociate into carbon dioxide and water.
But like, do I need to memorize that?
No, this middle part here, guys, don't need. You just need to tell me, if you see 2 H's like that, you just form carbon dioxide and water. Those are the products. Okay, can?
Okay, then do I need to memorize the HR part also? Like HR will become carboxylic acid, and then
you realize there's no need to memorize, right? Okay, because from what we do over here, I just follow the rules. You cut already, right? Double bond just add O, H just turn to OH. So there's no need, right, to memorize all this. Just follow the rules, right? And you can apply for anything. If I ask you to memorize, right, you cannot apply when I give you a big structure like this one to try. That's why I ask you guys, follow rules that are more specific. Then you'll never go wrong for whatever kind of structures that you get. Okay, so take a look at this structure. I want to try to draw this one now. Okay, we have 2 double bonds. So we must cut both. Okay, you cannot choose, okay, you must cut both. Yeah, how will cut? Again, to facilitate, okay, to see a bit clearly. I want you guys to label them. You want to call them A, B, you want to call them X, Y, you want to call them whatever, you give them names. Okay, but just go and label them, right? Perhaps I just call this A and B, and then call this C and D. Okay. Perhaps you can ask yourself, how many products do you expect to draw? Okay. Okay, all the A, B, C, and D are just follow the two steps. You will not go wrong. Okay.
Great.
Yeah, did B and C have anything broken in between? No, so B and C are together. Yeah. Okay, guys, how many products do you expect to get here? Okay, I take a compound, cut it 2 times, so you get how many pieces? Imagine you take a carrot, you cut the carrot 2 times, you get 3 pieces, right? Make sense? Just same thing over here. 1, 2, 3. You see that? Okay, the one on the left, what carbon does it have? Carbon A, obviously, right? Now the product in the middle, what carbons does it have? It contains both B and C. You can see that there's no segregation beyond that. Okay, and then the structure on the right hand side only contains compound B. Okay, just do slowly. Okay, A, B, C, and D. Yeah, organic chem is all about like puzzles on, if you realize. All these are like legit just mini games. Okay, it can be, it's definitely a more, to me, it's a lot more interesting than physical chem. It might look funny, that doesn't matter.
We are going to separate,
So what do you mean?
like separate like A and then B.
Yeah, I'm supposed to do that.
Oh,
I cut like that already, man. Right. It might look weird, doesn't matter. Just try the answer. Okay, go on. Try it.
Maybe.
Try this. Bro, then how you told me your degree is school. It's not even jungle in Malaysia. Don't even pack so much one lah. Doesn't matter, it's in school. If you go and make it, you can send, or just like go home and take or something. Go the nearby the star beside buy lah, this kind of thing.
Yeah,
Screw them, who's they? They, you know why? Okay, teachers they're like working adults, right? And then they just don't want to get complaints from parents. Later parents ask, not enough. You know, Singaporean parents, right? Very kiasu, right? Okay, then they'll be like, oh, it's not enough. Then they just eat as much as you want. Okay, bring 6 underwears or some shit. Yeah, then like then no parents will argue for that, right? If you just say bring 3, then the parents will be not enough, they not enough. They confirm complain to the teachers one. So you think this kind of thing is so that they don't get complaints, so they can rest.
No, but it's. It's just something is it a lot of stuff.
It's 4 days, probably needs 6. Otherwise, it's not going to make the whole thing very, very bulky, right?
But we have the top portion to make house, and it's bulky.
Okay, but like shirts and all that, you don't need shirts are not going to be that bulky as well.
5 shirts.
Okay, what? Shirts just roll, socks just roll up. Hang on. That's the part that makes it bulky. The stupid camp in school, it doesn't matter. Okay, come, let's take the answer.
Okay, thank you, bro.
Come, let's take the answer. Okay, carbon A, what does it become? It's just A alone, right? B has, what does it become? Okay, 2 H's like that, so what does it become? Okay, CO2 and water. Okay, so I want you to just write this down. We got carbon dioxide and water. That's for carbon A. Okay, just go and write all these carbons. Eventually, you all don't need to write all these A, B, C nonsense already. Okay, but you all already noticed just now that B and C are together, right? Okay, so I'm going to draw B and C first. Okay, B, the double bond must do what? Okay, B add an O to your double bond. And then it's going to connect to C, right? Go down and then go up, this C. C also has a double bond. What do you do to it? Add an O. What else does it have? B has H, right? So become OH. C has H, so also become OH. Yeah, that's it. This is a dicarboxylic acid. Both sides have carboxylic acid there. Okay, so that's B and C. Okay. How about D? Double bond O, just add a double bond, just add an O, then that's it. Yeah, that's the ketone. That's pretty much it. Okay, so if you want to do something, I'm just going to cut. Okay, and just practice, then you can. Okay, can? So that's that. Okay, we go through just, I think, 2-3 more pages, then 4 more pages, then we take a break first before we do the tutorial. Okay, next lesson I might need to continue with the tutorial as well. Okay, but come, take a look at page 32. Okay, not 32. 34. Okay. For page 34, just write this down at the bottom of the page again because there's a bit of space. But I'm going to explain what the notes have explained there as well. Okay. So that's basically, okay, I'm just going to draw another structure and we're just going to do the exact same thing, nothing new here. Okay, I'm going to draw this structure here. Just draw this. Okay, another dicarboxylate acid. A dialkene. Yeah. Okay, take a look. Okay, first of all, what do you do when you undergo oxidative cleavage? Cut which one? Both. Okay, cut both double bond O's like that. Okay, we are only going to label the carbons that are part of the double bond. So this is a double bond, I call this A and B. This is another double bond, I call this C and B. So you can all see all the 4 carbons happen to be relevant, right? Next. What's next? Okay, let's just do step by step. Okay, first of all, you cut 2 times, how many products are you going to get? Okay, take your carrot, cut twice, you're going to get 3 products. Right? Okay, so A, what's the product? Okay, it is at the 2 H's, right? Okay, so I want you to express it like this. Carbon A, right, will become carbon dioxide and water. Is there something else that's also similar to carbon A? D. D is the same thing. So we're right here, D, also carbon dioxide. Now at this point, right, in the carbon dioxide and water, I'm just gonna tell you guys Hail Mary ultimatum. When do we use carbon? When does it have carbon dioxide and water? You all realize the pattern so far. You see all the carbon dioxide and water from all our examples. Where is the alkene usually located at such that it gives carbon dioxide and water? Okay, I want you guys to observe patterns and you realize yes, carbon B at the end will give you carbon dioxide. Okay, this one don't have. This one, carbon A at the end gives you carbon dioxide and water. A and B are also at the end, right? So anything that's at the end, I want you guys to know this, note this from now on. This is known as a terminal alkene. Terminal means at the end, right? Again, like terminal illness at the end of your life, right? Okay, so same thing over here. Terminal alkene means alkenes at the end. These alkenes confirm will produce carbon dioxide and water, confirm. So next time you see alkene just hanging at the end, right? Only thing, right? Can see that? Okay. Okay, now we're concerned with B and C, guys. Okay, you all realize it's B and C separated? No, okay, they're together, right? Okay, so B turns into what? Okay, since they're together, B plus C, we put them together. So B is, you got O on the double bond followed by OH. Then link that to C. So C has double bond O also, then you add OH. Okay, but why am I going through this example? Why is there a dedicated segment in the notes to this structure? It's because this right here, guys, I want you all to write down the name. Okay, it's called ethane. Why ethane? Because I'm not done with the name. Ethane because there are two carbons, right? And then dioic acid. What's dioic acid? What does that mean? Okay, segregate the name like this. Yes, there's two. What's this functional group called? Double bond O and OH. It's called a carboxylic acid. So dioic acid just means two carboxylic acids. Ethane because there are two carbons. Each carbon happens to be a carboxylic acid. This is a very unique structure because you cannot write this structure in the exam. Okay, because this guy, what will happen is this. It will undergo further oxidation. It will further oxidize into 2 carbon dioxide and 1 water. So you need to write this instead in the exam. So whenever you all do your cutting, double bond O, OH and all that, the moment you spot this in your answer, you must change this into carbon dioxide and water, must erase this. It's just an exception. Okay, it's just this guy that will turn into carbon dioxide and water. It's just an exception. You just need to know this exception here. So guys, at the end of the day, this product here, this compound here, what does it give after undergoing oxidative period? It only gives you carbon dioxide and water, right? See, A, D, B, and C all just carbon dioxide and water. Okay, but more specifically, I'm focused on this guy here. Okay, so we learn 2 things, ethane dioic acid and the idea of terminal alkenes. All good? Okay, we're gonna try some questions, okay, before we take a break. Okay, one page of questions. Okay, then we take a break. Okay, page 35 first. Another oxidative cleavage question. Just go and try that. Right, okay, let's go through. Okay, so I'm going to cut the 2 bonds, and I'm only concerned with all the carbons in the E double bond. So A and B, C and D, for example. Okay, so what should I do here? How many products am I going to get? Okay, this time I only get 2 products. Okay, we do the A and C first. So what I want you to do, before you do any O's or anything, right, you can just draw out that fragment. You can see that. And then the bottom fragment, can you all see, looks like this. So what I've basically done is I have cut, and that's all I've done. I just cut the thing into 2 pieces. I cut it already, then I just pull it out. Can you all visualize? If I put this back, I'll just attach it there. Okay, now then we need to add all the oxygens and whatnot. Okay, so all the double bonds must do what? O, and O. Okay, next. Check for H's. Okay, any H here have turn into OH. H, OH. H, OH, all also have. Is that our final answer? Okay, what else do we need to do? Okay, you all notice that this is the unique structure, ethane dioic acid. So you must write what instead? Okay, 2 CO2 and water. Now, why is there 2 carbon outside? It's because there's only 2 carbons now, obviously. Yeah, okay, then water will balance it out. So your structure should be this. Now, let me just give you guys a small little tip, right? For when you can spot such structures. Okay, so you all notice something. You will see ethane dioic acid whenever there is a double, single, double pattern. Now, this is not it's not like the savior of everything. Okay, sometimes it wouldn't work, but generally speaking, if you see double bond, single bond, double bond, this mixed pattern, you will probably going to form ethane dioic acid. Okay? Can? Double, single, double, double, single, double. You're probably going to form this, so you're going to see carbon dioxide and water. I'll give more examples later also. All good? Can? So yeah, anyone who struggled with the first, this one? Okay, okay, so a general tip is this. I suggest you all snip here, then just pull it out, like what I did. Then you add the whole separately. Okay, that one will be good if you want to visualize. If no questions, we shall take a short break. Okay, then we shall come back in about, okay, we have not much left to cover. I think tutorial we have to cover next lesson. Okay, we come back in like 8 minutes now. Okay, so by like 6:47 around there. Okay, for those on Zoom. Okay, we're just gonna finish up some of the questions that we have here. Okay, but before we look at the next page questions, right? Okay, let's just try one more structure. I mean more practice good, right? Okay, so I'm gonna draw the structure here, and I just need you guys to draw the products. Yeah, okay, just go and try. You just write this somewhere like. Yes, oxidative. Okay, okay, so let's draw this up. Okay, again, we got cut 2 here. 1, 2. Okay, so we got A, B, C, and D. They all happen to be each other. Okay, so we have 3 products, right? Carbon A there. Okay, you should get this here. Right? Okay, that's for structure A. How about B and C? Notice that the B and C follows the double, single, double pattern. Even if you draw out using the rules, you must change it to carbon dioxide and water. So 2 CO2 and H2O. Okay, these are both your PNs. Okay, then finally we got structure D. D is just the far right over here. So double bond O, 3 carbons. Okay, check you got 3 carbons, and then your carboxylate acid. Structure D. All good? Okay, the more practice we do here, the more you get this faster. Okay, so get turn over to page 36, and I want you all to look at this pattern. Okay, I'll just kind of okay, the hint is already given. Okay, so give it a try. Yeah, some carbon you didn't come right. Do you need any notes? Because the notes in day one, because before you join, any of the notes you need to print. Because I think I printed one them. Yeah. Or do you print yourself? Because I know Esther print herself. Yeah. Yeah, you want to use iPad? Okay. Your draw skeletal, your draw structural, both are acceptable. Okay. Think you'll get the idea here. We are supposed to combine the products now into the original alkene. Okay, so if you realize all you need to do is just to reverse the 2 steps. Remove all oxygens because you're reversing the oxidation, right? Remove all oxygens and then just join together the double bonds. If you need some assistance here, right, you can always write numbers. Okay, let's just say, I think some of you all do this skeletal, right? Okay, I'm going to convert this into the skeletal first. So it looks something like this, correct? Is that? And then this one is here, 2 carbon, 1 carbon, right? Okay, so all you need to do here, remove all the oxygens. So I'm going to remove one here, and here. So now it's just a normal H, and H is usually just invisible, right? For skeletal formula. So do this and then just attach them together. Okay, so I'm just going to do all this like that, like that. So make sure you have the correct number of carbons. You should have 1, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7. Okay, that's the answer here. Okay, it's just working backwards now. All good? Okay, I want you to try question 2 now on page 37. Suggest for the part B structure, I'm going to draw all the bonds also, or convert to the skeletal formula. Okay. So we still have time for the tutorial. Okay, gonna review the answers. Okay, that's for structure A. Okay, take note, okay, I know there's a big prank here. You should have two oxygens here. Each double bond must have one oxygen. They are actually separated, it's just that a bit no space. Okay, so you draw a bit bigger also. Okay, so if you realize I only have one product here, as you can tell, you cut the ring once, you still get one product. Right? Second thing over here, okay, this one I think shouldn't be a difficult question also. Copy out the rest because they're not part of the double bond. This one just becomes C double bond O, OH. This one carbon dioxide one. Okay, can? Open. So getting a bit used to this, any questions? Okay, we started a bit late just now, so I want to do like maybe one or two tutorial questions first. Okay, if you all look at the last segment of the notes, it says that distinguishing test. I won't be going through it here. I feel that the questions at the back as well, right? It's a bit advanced for our current stage, so we won't be doing this yet. Perhaps in the next lesson. Okay, so what I want to do now, right, is the tutorial. Okay, we still have about 10 minutes. Okay, so take out the tutorial, right? I want to try maybe let's do like 2 questions. Okay, or perhaps let's maybe do 1 question now. Okay, we're going to do the question over here, the first one. As you can see, they've given us a structure, and you need to just react with all the different regions and conditions there. Okay, of course, at this stage, okay, you might need to refer to the notes and go ahead. Okay, but the key here is to draw the same product, but for a lot of them, right? Yes, okay, let's just do everything. Can. Slowly go ahead and check. That's for anyone needs paper?
Wait, Kaishan, what questions again?
The tutorial, the first question.
Okay.
Try as many as you can. Okay, I know the question asks you guys to describe all observations, but we skip that first. I know observations because you can just copy straight from the notes. I don't think that's very important. I'm more concerned with the products from each of these parts here. Okay, so don't care about observations. Just draw the skeletal formula for all these guys. Right? You can do everything. Okay, don't anything you don't know, just skip. Then just move on to the second one. Right? And Esther, we don't need to draw the mechanism. Okay, guys, we don't need mechanism here. Don't need balance equation and nothing. I just want to see the final product. Final product for each category. If not, it takes too long. Yeah, okay. Yeah, you see two double bonds here, right? So you need to react the same twice. No? Like for example here, right? Okay, we do Br2 is C cell. Okay, how about this one? H2 gas, what's this reaction here? Reduction, right? You reduce the alkenes into alkanes, so it's just this one. That's the answer. Br2 is CCl4, what should we do here? You have to, what reaction is this called? Okay, good. Electrophilic add. So you see two double bonds, you need to add for both. Okay, so for this one, remember you're adding two bromines, so you add one over here, one over here. Okay, reference to the original structure. And then, where else? Here as well. Okay, so add bromine here, bromine here. Yeah, again, it looks very contrasted, but yeah, that's the idea. Okay, then just repeat the same thing. Every single reaction here will repeat twice. Yeah, see, I will just react here and here. It's two separate alkenes. Okay, alkene here, remove double bond, then just add. Remove double bond, add. Of course, I do very long already, sorry. Yeah, don't need your mechanism and all that. Okay, you all can just look at the final product. Okay, only part 3 is a bit more tricky. I fool with that. Okay, we want the major product. Always. At some point, we don't need to say already, must assume. Okay, for Br2 aqueous, we need to be careful with the Br and the OH. Okay, when refer to what we did just now. Okay, how do we form the major product? Where does the OH go and where does the Br go? Right? So I'll go through part 3 right after this. Okay. Okay, come. We look at part 3 first. Okay, I want to talk about this because you'll notice in part 2, right? It doesn't matter where you put your bromine because they're both bromine, right? So they're just gonna get attached. But for part 3, remember for Pr2 aqueous, what are you actually adding onto the alkene? Are you also adding 2 bromines? No, you're adding 1 bromine and 1 OH. Okay, but it now matters where your bromine and OH goes. So remember, we are drawing the major product, so we need the most stable product to form. Taking a look at the two alkenes here, let's look at the first one, this alkene. Okay, just follow me on the board here. This alkene here, you can either put Br and OH like that, so Br then OH. Which one is correct? Okay, remember, guys, when you first attack the electrophile, okay, take this alkene, when you first attack the electrophile, this is what electrophile. What are you actually attacking first? Remember from just now? The alkene must attack Br with the partial positive charge, right? Okay, so from that alone, that means your product will have the bromine somewhere. Okay, take a look. Where does the bromine go? This carbon A or carbon B? Which one? Okay, if not sure, let's check. If the bromine goes onto carbon A, then this carbon must have what? The positive charge, right? Okay, on the other hand, you can do the other one, right? Okay, this if the positive charge is here versus the positive charge here, which one's better? Where should the positive charge be? At the bottom or at the top? Okay, good. That's why I tell you guys to do this a bit faster, you can look at where the positive charge can go towards. Always place the positive charge in a place where you have more alkyl groups. So this is what kind of carbocation? Tertiary. 1, 2, 3 carbons attached to the plus. If you put a plus here instead, then what will happen? See, erase, do again. If the plus charge came here, that means the bromine must have come here. This is a what? Carbocation. Secondary, only just 1 and 2. And again, which one is more stable? Tertiary. That's why now you're gonna place the bromine at the top and the what at the bottom? Must be the other one, which is OH. So we do the same thing for the right hand side. Okay, take a look here. Okay, we're looking at these 2 carbons. Okay, so where should the positive charge go towards? Should it come here at the top or in the middle? The plus charge must be in the more congested area, right, which is in the middle. So that means the top here must have what? Br. And in other words, you must change the plus now to what? What's the final product? Put the OH there. So perhaps you want to work out the plus charge first. Go and play around the plus charge position. Okay, then you have to try the same thing for both part 4 and 5. Okay, so suggest just do part 4 and 5, right? Then we stop here for today. Okay, finish up the 4 and 5. Then I'll go through. Okay, we will need another lesson, right, to do a tutorial, okay, because there are other types of organic questions I need to expose you guys to. Okay, so we shall do that on the next lesson. Right? Okay, have you all done part 4 and 5? Can I go through those two? Okay, I'll just go through those two since you all done with that also. Okay, the rest, okay, you all can go and try on your own time. Okay, continue next lesson. Okay, so just finish this by next lesson. Okay, come, let's look at part 4. HBr. Again, it matters where the H and the Br goes, right? Okay, so how do we do this? Okay, let's do the first one here. Okay, it must attack what? H or Br. The alkenes must attack H. H has the partial positive charge now. So that means the H. Okay, where must the plus charge go towards? The bottom, right? The more congested one, that means here must have what? The H. That means here must have the Br. Yes. Okay, repeat the same thing for this side. This exercise will train you guys to see more fast, quicker. Alright, okay, so take a look at this one. Where should H go? The top or the bottom? H must go towards the top. Then the bottom has the plus charge, right? Which eventually is now the bromine affects the plus charge. You see that, right? And same thing, no matter what they give you, look at IBR. IBR, what the partial charges here? I has the partial plus, right? Okay, the closer you are to the top. Okay, remember FCl, I. F being the most electronegative, the closer you are to him, the stronger you are in terms of electronegative. So I is more electronegative than Br. So that means I is the electrophile, right? So look at this one. I must go towards where? The top, so that here we'll have the positive charge, right? Which then eventually is the Br over there. Okay, good. How about this one? I is on the top, Br at the bottom. Yes. Okay, so you will eventually, right? You can see this very quickly. It's all an exercise for practice. Okay, can? Alright, so with that said, you can go and finish up the last 3 parts. We can go to the next lesson. But remember, next lesson we're going to bring the Alkenes tutorial and the notes also as well. We have to do a lot more questions here. Okay, if not, if we just do the notes, it's a bit pointless. Okay, so I don't move on to arenes yet. We just do this for next lesson. Okay, so that's it for today. Alright. For next week, you need to see. I don't know when are you guys free. Because I know this week you all have the camp, right? Yeah.